Okay, here we go with the review for Chapter 9, Acids and Bases. Things that you need to know. Okay, so first up with theories. We have Arrhenius. That was the center of the bullseye. Remember that Arrhenius defined acids as H plus donors and bases as OH minus donors. This is also known as neutralization reaction. That is because when we have H plus given in something like HCl as our acid plus NaOH, which can donate an OH, making it our base, we're going to react that with OI, outsides and insides, so H and OH are going to go together and make water, and that, of course, is water. We don't have another name for it. Plus, the insides are going to go together, making NaCl, which here is a salt. Now, not all salts are created equal. Salts can be acidic or basic, depending on how they react with water around them. The key here is if the salt then reacts with water and makes a strong acid or a strong base, then it is neutral because it will automatically produce strong acid, strong base, and go back to ions. But if the salt, say, is something like NH4OH or NH4Cl, so it separates so you get NH4, and that goes with water, then what we get over here is NH4OH plus H plus. Well, this right here is a weak base, but this causes the water to be slightly acidic because it's an acid. Now we could do the same thing with a base. Say that I had, so this NH4 could have come from an NH4Cl or Br or even a nitrate or sulfate. Say that I had instead something that's going to, say, Na2CO3. Well, out of that, Na is soluble all the time, so it's going to go away, and we're going to be left with CO3 with a 2 minus. Now, that's going to react with water, and remember I only move one hydrogen at a time because this is going to be a Bronsted-Lowry reaction. Therefore, I get HCO3 with a minus, plus what else is left over? The OH minus. So here I end up with basic salt because this is a weak acid and it won't separate. I hope that helps you understand when we have a salt, we could have acidic salt and we could have a basic salt, but you got to combine them with water and see what it will make. Okay, so the second one that we need to worry about is the Bronsted-Lowry. Remember, with Bronsted-Lowry, acid was an H plus donor and base was the H plus acceptor. Now the key here is you're not going to get a neutralization reaction, but you're going to get things on the product side that have charges. Okay, so that's the key here, is you're going to look for charges in the products. Now, usually on this type, you might have one strong acid or a strong base that you recognize, but you won't necessarily recognize what the other is. So you have to look at what is happening in the reaction. So I could take HCl and put it in water, and what's going to happen is I'm going to end up with H3O plus Cl minus, because remember, HCl is a strong acid, so it's going to split. Then that H plus is going to be picked up by the water. So we know that this is an acid. That makes the water here, because it's amphoteric, meaning it could be an acid or a base depending on who it's with. Well, it's with an acid, so it's going to act like a base. That means over here H3O is going to be our conjugate base, our conjugate acid, sorry. And Cl minus is going to be our conjugate base. That ran out of room, sorry about that. Okay, But what you're going to need to be worried about here is they're going to ask for the forward reaction, and RxN is just my shortcut to say reaction. What is the acid? Well, what would you say? If you said HCl, you were correct. And then the base for the forward reaction would be H2O. So they could also ask for the reverse reaction. And if I did the reverse reaction, then I would have the acid, which would be H3O plus, and the base, which would be the Cl minus. Okay? So pretty straightforward. Now, as we look at this, HCl and Cl, these two right here, are known as conjugate pairs. And also the water and the H3O are also known as conjugate pairs. One side they're the acid, the other side they're the base. Okay, I'm not going to spend a lot of time on this because we've done a couple worksheets and hopefully this has come very easy to you, but it might be something you might want to put on your card because you need to go back and forth between all of these. You need to be able to figure out what the pH is, what the pOH is, what the concentration of hydrogen is, and the concentration of hydroxide. You also need to remember that if your pH is greater, if your pH is greater than 7, then you've got a base. If your pH is equal to 7, then you are neutral. And if your pH is less than 7, then you're acidic. Now, or an acid. Please be careful with this. It's pH, not pOH, and they'll try and trick you. Make sure if they give you an OH that you go up through the pOH and then over to the pH. Okay, remember that pH plus pOH equals 14, so it's a real quick and easy thing to do. But you need to be watching and not just jumping when you do the minus the log of something, thinking that's what the pH is. Make sure you're finding pH and not pOH. Okay, we need to define strong and weak for acids and bases. So let's talk about strong. Strong acids will 100% dissociate, whereas weak acids and bases will 1 to 5% dissociate. So, don't think concentrated. Concentrated is different, but weak and strong just means how much they will dissociate in water. Strong dissociates 100%. Weak, 1 to 5%. Now remember we have our tricks for our 6 strong acids and bases. The strong acids are swoop and down, and the swoop is the oxyacids, and the 3 oxyacids are HNO3, which is nitric acid, H2SO4, which is sulfuric acid, and HClO4, which is perchloric acid. Then we have our binary. Binary means just 2, and that starts at the Cl, so we have HCl, which is hydrochloric acid, HBr, which is hydrobromic acid, and HI, which is the friendly, not so friendly acid that will tell you hi but eat you alive. It's hydroiodic acid. Notice the difference here. On oxyacids, we take the polyatomic. For HNO3, it was nitrate. 8 goes to ic, and we add acid. Now, if the ending of the polyatomic was an ite, remember, I gave you a little trick for this. 8 is like Thanksgiving dinner. I love it. I eat too much, and about an hour later, I'm sick. So 8 goes to ic, and then you add acid. Ite reminds me of fight, like you're going to fight somebody. And how many does it take to fight? Oh, it takes 2 of us to fight. So ite goes to us. If you have polyatomic that was an ite, it would go to us, and then you add acid. Binary, on the other hand, you add the hydro in front to represent the hydrogen, do the base name of whatever hydrogen's with, add ic and add acid. Now you need to do the naming, so that's why I'm sort of going over this. Now these are the acids over here that we just talked about, the 6 strong acids. And then the 6 strong bases, if you'll remember, are in the tetras pattern. So I'll just do this, okay? They're the 3 and then slide over in 3 for on the alkali and alkali earth. So if we start, it was LiOH, NaOH, KOH, then you slide over and you get calcium hydroxide. Whoops, sorry, I'm moving it again. Strontium hydroxide and barium hydroxide. Now I didn't write the names of these out, but I think you could handle that. Alright, so I need to know my 6 strong acids, 6 strong bases. Most hydroxides, by the way, will dissociate in water. A lot of them are not soluble or don't like to be soluble, but most of the Arrhenius ones are fairly soluble. Okay, so when we look at polyprotic acids, the strongest one is always the first one. Now strong for weak acids, so like, okay, so as we look at polyprotic acids, in the blue I've got phosphoric acid. Now every time I take off a hydrogen of a weak acid, I'm going to be left with an ion. And that anion is going to then go to the next one and keep giving off one hydrogen at a time until all the hydrogens are gone. Well, the last hydrogen I give off before they're all gone, that acid right there is the weakest. So if I'm looking at this one right here is my weakest acid out of all the 3 on the left in the blue. Now if I look at the next one, we know that H2SO4 is a strong acid, so we know it's going to give off a hydrogen, but it only gives off one that's strong. The second one, the HSO4-, that's actually a weak acid, and it doesn't like to give off that last hydrogen very well. Okay, so we've done several titrations, so you should be very familiar with titrations. You need to know that the equivalence point is where the hydrogen ion concentration is equal to the hydroxide ion concentration. That's where we got the inflection point of the graphs. Now, if the acid was equal to the base as far as their equivalence, meaning how much hydrogens or hydroxides they could be given, then we'll just call it EQs. Then we could use the equation M1V1 equals M2V2. And that's if their equivalents were equal. Now, if they're not equal, then we have to be able to figure out the number of equivalents and sort of do a little bit of stoichiometry. So we need to be able to figure out the number of equivalents something has. So for instance, in BaOH2, that would have 2 equivalents. Now I can also find what they call microequivalents if I've got a very small number. Remember, milli means 1,000, and micro means 10 to the minus 6. But I can also find that. So if I've got a very small number, or if I've got a concentration, the first thing I need to do is change that to our favorite old friend, the mole. Once I've got it into moles, then I can see how many equivalents there would be. So we need to be able to go back and forth there. We can also do that with the salts. Remember, we'll need to know that. Okay, then we talk about buffers. And buffers are really important, remember, for our body and our systems in our body. They do an important job. They hold the pH steady till they break. Now, if we drink too much alcohol or we drink too much water, we can actually break our buffers. They can't hold anymore. And then we run into problems. So, what is a buffer? Well, a buffer is a weak acid or a weak base, and it's salt. So when I talk about that, what we're worried about here is the weak acid is going to neutralize any base that's added up to the point where it will break. The salt, actually the anion of the salt for a weak acid, or the cation for a weak base, an anion will actually is a base here, and it will neutralize any acid that is put into the system until the buffer breaks, until I don't have any more of the salt left over to take care of that. Now, I believe that's all that you need to know for the test. Now, I want you to make sure that you know how to do every single bit of this, and if you don't, you better come see me. And good luck on the test.